A 2019 study from Oregon State University measured something extraordinary in suburban soil. Researchers analyzed nitrogen levels beneath patches of a common pink-flowered plant that homeowners spray with herbicides every spring. The soil contained 40% more bioavailable nitrogen than adjacent grass. The plant was producing fertilizer from thin air. This wasn't a laboratory experiment with engineered bacteria. This was a wild plant doing what it had done for millions of years, converting atmospheric nitrogen into soil nutrients through a symbiotic relationship with rhizobium bacteria. The mechanism is elegant. Root nodules house nitrogen-fixing bacteria that transform N2 gas into ammonia compounds. The plant feeds the bacteria sugars from photosynthesis. The bacteria feed the soil nitrogen. Everyone wins except the chemical fertilizer industry. Yet across America, millions of gallons of glyphosate are sprayed annually to eliminate this biological miracle from suburban landscapes. The plant enriching the soil is classified as a weed, removed and replaced with grass that requires synthetic nitrogen applications. The system is backwards. The plant performing free soil enrichment is Trifolium pratense, known commonly as red clover. Red clover belongs to the Fabaceae family, the legume lineage that mastered atmospheric nitrogen fixation roughly 60 million years ago. This evolutionary innovation changed terrestrial ecosystems permanently. The nodules visible on clover roots are not tumors or disease. They are biological reactors containing billions of rhizobium bacteria. These bacteria possess the nitrogenase enzyme, one of nature's most complex molecular machines, capable of breaking the triple bond of atmospheric nitrogen. The process requires enormous energy. The plant provides 12 or 16% of its photosynthetic output to fuel bacterial nitrogen fixation. In return, the bacteria deliver 100–300 pounds of nitrogen per acre annually, deposited directly into the root zone. When the plant dies, this nitrogen becomes available to surrounding vegetation. This is not fertilizer application. This is atmospheric chemistry performed by living organisms, creating fertility from nothing but air, sunlight, and soil. Modern agriculture spends billions manufacturing synthetic nitrogen through the Haber-Bosch process, an energy-intensive industrial method invented in 1909. Nature solved the same problem 60 million years earlier, quietly, for free. The red clover does not demand patents or petroleum. Historical records from medieval Europe document red clover as a cornerstone crop in rotational farming systems. English agricultural texts from the 1600s describe clover lays, fields planted with clover specifically to restore nitrogen after grain harvests. Farmers understood empirically what science later confirmed. Clover-enriched soil produced heavier wheat yields the following season. This knowledge predates chemical fertilizers by centuries. Irish farmers rotated clover with oats and barley, maintaining soil fertility without external inputs. German agricultural manuals from the 1700s detail clover cultivation techniques, emphasizing the plant's capacity to renew exhausted land. The practice was so widespread that red clover became embedded in European pastoral imagery, the classic meadow scene with grazing livestock among pink flowers. But clover's value extended beyond nitrogen. The flowers attracted pollinators, supporting honeybee populations critical to orchard yields. The deep taproots broke compacted subsoil, improving drainage and preventing erosion. Livestock grazed clover pastures, converting plant protein into meat and milk while depositing manure that further enriched fields. The system was cyclical, regenerative, self-sustaining. Then industrial agriculture arrived with synthetic fertilizers, monoculture grain production, and the concept that biological complexity was inefficient. Clover went from agricultural asset to suburban nuisance in less than a century. The modern American lawn industry operates on a simple economic model: sell chemicals to maintain a monoculture. Red clover disrupts this model completely. First, clover spreads aggressively through rhizomes and seed dispersal, competing with turf grass. Second, Clover's nitrogen fixation reduces dependence on synthetic fertilizer applications, the industry's primary revenue stream. Third, Clover's deep tap roots resist drought better than shallow-rooted grass, reducing irrigation needs. Fourth, Clover flowers attract bees, which suburban aesthetics classify as undesirable. The lawn care industry's solution was brilliant: reclassify clover as a weed. Marketing campaigns from the 1950s onward portrayed the perfect lawn as pure grass, uniform green, devoid of flowering plants. Herbicides like 2-Coim-4-D were developed specifically to kill broadleaf plants while sparing grasses. Clover, with its trifoliate leaves and nitrogen-fixing abilities, became target number one. Homeowners were trained to view pink flowers in their yard as failure, not free fertilizer. The distinction between lawn and weed is not botanical. It is economic. Clover was eliminated not because it damaged soil, but because it threatened profit margins. Beyond nitrogen fixation, red clover synthesizes bioactive compounds for defense and reproduction. The plant produces isoflavones, phytoestrogens including genistein, didzine, biochanin A, and formononetin. These compounds deter herbivores while providing structural support to cell walls. Red clover contains significant concentrations of vitamin C, with fresh leaves measuring 80–120 millinanomoles per 100 dry weight. For comparison, this matches the vitamin C content of raw bell peppers. The mineral profile includes calcium, 200–300 millimoles per 100 grams, magnesium, potassium, and trace amounts of selenium. Historical European populations consumed clover leaves in salads and soups during spring, when fresh greens were scarce. Medieval herbals documented these practices, framing them as seasonal dietary supplements rather than medicine. However, modern understanding reveals complexity. The same isoflavones that protect the plant can interfere with thyroid function in excessive quantities. The plant is not benign. It is chemically sophisticated, producing compounds with genuine biological effects. This information is presented as botanical fact, not dietary recommendation. The chemistry exists independent of human consumption patterns. Nature does not design plants for human benefit. We simply encounter the results of millions of years of evolutionary biochemistry. Red clover flowers from May through September, producing tubular pink to purple florets rich in nectar. Each flower head contains 50–100 individual florets, creating dense nectar resources across blooming meadows. Honeybees, Apis mellifera, visit clover extensively, though their short tongues struggle to reach nectar in the deepest florets. Bumblebees, Bombus species, possess longer proboscises, making them more efficient clover pollinators. A single acre of red clover can support dozens of bumblebee colonies, which in turn pollinate surrounding vegetable gardens and fruit trees. This ecological relationship has agricultural consequences. Farms with clover borders report 30–40% higher yields in bee-pollinated crops compared to monoculture operations. But suburban lawns eliminate this dynamic entirely. Herbicide applications remove clover, reducing available forage. Reduced forage means fewer pollinators. Fewer pollinators means declining yields in home gardens and nearby orchards. The homeowner then purchases pollinated fruits and vegetables at grocery stores, often trucked from industrial farms hundreds of miles away. The system exports fertility and imports food. Meanwhile, the free biological infrastructure, nitrogen-fixing plants supporting pollinator populations, sits dormant in chemical company warehouses, bottled as selective herbicides. We pay to destroy what we should cultivate. Red clover develops a substantial taproot system, penetrating 2 to 4 feet into soil profiles. These roots perform mechanical work that shallow-rooted grasses cannot, breaking compacted subsoil layers, creating channels for water infiltration, and aerating deep horizons. When taproots die and decompose, they leave vertical pores that function as drainage pathways during heavy rainfall. Compacted suburban soils, crushed by construction equipment, foot traffic, and neglect, benefit enormously from this biological tillage. Yet lawn maintenance actively prevents it. Herbicide treatments kill clover before taproots establish. The result is hydrophobic surface soil, poor drainage, waterlogged grass, and homeowners installing French drains to solve problems that clover roots would address naturally. The irony deepens. Clover's drought tolerance exceeds turfgrass significantly. During summer dry spells, clover remains green while surrounding grass browns and dies. This occurs because deep taproots access moisture reserves beyond the reach of grass roots. Homeowners respond by increasing irrigation, raising water bills, depleting aquifers. The free solution grows on the lawn's edge, classified as a weed, sprayed with chemicals, removed. We have engineered landscapes that require constant intervention to maintain what clover provides autonomously. The grass is not greener, it is simply more expensive. Red clover establishes readily from seed, germinating within 7 to 10 days in soil temperatures above 50 degrees 10 degrees C. Optimal sowing depth is 1/4 inch, broadcast across prepared soil or mixed with grass seed in lawn blends. Once established, the plant self-seeds prolifically, with mature plants producing 500 to 2,000 seeds per season. Seeds remain viable in soil for 20-plus years, creating persistent seed banks that regenerate meadows after disturbance. The plant tolerates a wide pH range, 6.0–7.5, and thrives in full sun to partial shade. In agricultural contexts, clover is mowed or grazed to prevent flowering, maintaining vegetative growth and maximizing nitrogen fixation. In ecological contexts, flowering is encouraged to support pollinators. The plant requires no fertilizer, producing its own nitrogen renders synthetic applications redundant. Pest pressure is minimal. Clover's chemical defenses deter most herbivores, though deer browse it occasionally. The primary threat to clover is herbicide, specifically broadleaf targeting compounds applied to lawns. Without chemical intervention, clover persists indefinitely, spreading slowly through rhizomes and seed dispersal. This is not invasive behavior. This is ecological succession in action, a nitrogen-fixing pioneer species preparing soil for diverse plant communities. The system requires no human management, only the absence of active destruction. Every spring, red clover returns to lawns, sidewalk cracks, and neglected fields despite decades of herbicide campaigns. The plant endures because its biology is fundamentally sound: nitrogen fixation, deep roots, prolific seeding, pollinator support. These are survival strategies refined across millions of years, immune to marketing narratives about lawn perfection. The question is not whether clover belongs in the landscape. The question is why we spend billions annually fighting a plant that improves soil, supports pollinators, and requires zero inputs. The answer involves fertilizer sales, herbicide markets, and the monetization of ecological ignorance. But knowledge shifts power. Understanding clover's nitrogen-fixing capacity, historical agricultural value, and ecological contributions transforms perception. The weed becomes infrastructure. The nuisance becomes asset. Homeowners allowing clover to persist participate in a quiet rebellion against chemical dependency, restoring biological function to sterilized landscapes, one lawn at a time. The revolution requires no tools, no products, no purchases. It requires only the decision to stop destroying what nature provides freely. Red clover was never the problem. The system eliminating it was.